Let me say something about the plan of the 4 talks. So I'll be talking about smoothings of complex normal surface singularities. And the plan today is just to talk about normal surface singularities, to give you an idea of the main examples, the main properties, what we look for, what we're interested in studying, just about the singularities themselves. And then tomorrow I'll start talking about smoothings and deformations, and that will be preparatory for the main lectures, the last 2, where I talk about the 2 particular topics. One of them is rational homology disk smoothings, smoothings with Miller number 0, and the last lecture about some relationship between so-called Miller numbers and Tiurina numbers. So let me start out with just reminding you the kind of thing we'll be talking about will be a germ of a complex normal surface singularity. So we're only interested in the small local properties of a singular point, not in some general affine birational question. And that's what NSS will mean. And normal, the normal will mean the singularity is isolated and Cohen-Macaulay. So the local ring is going to be Cohen-Macaulay. But let's start out with the first example we want to think about, which is suppose you have a polynomial in 3 variables with an isolated critical point at the origin with f of 0 equals 0. And for that polynomial, the hypersurface has a singularity at the origin, and so we'll let v comma 0 be the germ of the hypersurface. But we want to look at it locally, so we'll intersect with a small 5 ball. And this germ is what will be our first example. So some good examples we might call VPQR, where you just have where the polynomial is x to the p plus y to the q plus z to the r equals 0. We'll be interested in studying that locally. That obviously has an isolated singular point at the origin. And the first interesting definition we'll make is the so-called link of the singularity, link. So that's where we take this complex hypersurface with a singular point, and we intersect with a small 5 sphere. We intersect with a small 5 sphere, and we call that sigma. And so this has complex dimension 2, real dimension 4. We've cut down by dimension by intersecting with the sphere, and we end up with a 3-manifold called the link. So here's a picture. So here's what here's f equals 0. And but then when we intersect with the ball, the part we see is, I should be using some colored chalk here. The part that we see in the intersection is here and here, and so that's the link sigma. So this is a compact, oriented, and especially connected 3-manifold. So this is some connected, compact 3-manifold. And one of the reasons that this is interesting is because the way that the singular hypersurface sits in the ball is the cone over the way that sigma 3 sits in the 5 sphere. So the pair of the ball and the hypersurface, that's the cone over the pair consisting of the 5 sphere and this 3-manifold. So sigma is a 3-manifold, and it's a knot in the 5 sphere. So this 3-manifold sits in some complicated way in the 5 sphere, and that's basically telling you what the singularity looks like. So when you study knots, in the three-sphere, knots are just circles. Their intrinsic topology is uninteresting. However, in this case, a sigma is interesting. In the following sense, it's the subject started with a theorem of Mumford in 1960 that said that the sigma is not simply connected. Pi 1 of sigma is not the identity, assuming this really is a singular point, if V is really singular. So that means the three-manifold by itself, the link, is saying something interesting about the singularity. So how do we know, how do we decide what to do with sigma? How can we see what it is? Well, we do that by resolving the singularity. So you should know that there exist resolutions of singularity, so we're just interested in locally there. So we want to consider a good resolution. I'll say what that is. Pi from v twiddle comma e into v comma 0. So what's a good resolution? So first of all, pi is a proper map, and pi maps v twiddle minus e isomorphically to v minus 0. And when I should have said here, v twiddle is non-singular. So we have a non-singular surface, a configuration of curves, and the curves get collapsed down to a point, and off the curves this is an isomorphism. And the second part is that E is going to be a union. This is a pi inverse 0. This is going to be a union of non-singular curves intersecting transversally. EI is non-singular. And we have this symbol means transverse intersection. Okay, so it's been well known for over 100 years that surface singularities have resolutions. You can make good resolutions. What's it look like? So let me draw you a picture. So I'll just draw the curves. So this is what E will look like. And what data is there besides the way the curves intersect? Well, these guys have a certain genus. So maybe in square brackets I'll say this curve has genus 3. And so each EI is a compact Riemann surface, but it's also a compact surface sitting in a smooth surface, so it's got a normal bundle. So the normal bundle of EI in v twiddle is going to be some integer which we'll call minus di. Turns out it'll be negative. Okay? So you can read this, so you can, if you have a good resolution, this is the kind of picture you have. Now, why is this a good thing to do to understand the link? Well, let me get another piece of chalk here. That's because we're taking the singularity and we're looking at some distance from the origin, epsilon distance from the origin. So in this picture, we should be looking at the boundary of a tubular neighborhood of the curves. So we consider the boundary of a tubular neighborhood. So let me draw you a picture. So let me extend this over here a bit more. So we'll look at the boundary of a tubular neighborhood. So the picture will be something like this. So I'm going to go out some distance epsilon from the curve itself on this now non-singular surface. And you can see the boundary of this is a three-manifold. So sigma is the boundary of a tubular neighborhood of the curve, right? So We're looking at the points that are of distance epsilon from the singular point. That means distance epsilon from the curve. So this picture actually tells us what the topology is. Tells us what the topology of sigma is. You take all these tubular neighborhoods. So for each curve, you would take one tubular neighborhood and a tubular neighborhood here, and then you perform some plumbing operation. So you get sigma via plumbing. So there's, you might call this kind of piece here where they curve, where they cross, a plumbing fixture. So what that means is that this discrete combinatorial data allows you to build the three-manifold sigma. So sigma is a very special kind of three-manifold. It's a very friendly kind called a graph manifold. Sigma is a graph manifold. So there's a general theory due to Thurston and others about three manifolds. It's very complicated. These are easy from this point of view. You can build these things from discrete data. The way we're going to picture this configuration of graphs, however, is a dual one by called the configuration we want to consider the weighted dual graph. The weighted dual graph. So what that means is we're going to let EI, each exceptional curve, correspond to a vertex. And intersections, EI intersect EJ, will correspond to edges. So we'll transfer this picture into a graph. And so what would it look like? It'll be something like this. So there's this guy over here of genus 3, which is probably over here. I'll put a genus 3 over there. And maybe this curve here had self-intersection -6. This curve, so we put a -6 over there. And we translate this configuration into a dual configuration, and we call this the graph. Okay, graph gamma. So to summarize, we resolve the singularity by a good resolution. In dimension 2, there's something called minimal good resolution. So there's a unique way to do this. And then the way the curves fit together, we encode by information in some graph. Okay, so that's our first. That's the first assignment that we're going to make. So the graph will be decorated by degrees of normal bundles and the genus of each curve. So most of the cases we do, these curves will have genus 0, but could be anything. That's what the graph is going to be. So let me say a few things about this graph. So first of all, this weighted graph has an intersection matrix, EI dot EJ, called the intersection matrix. You can read that off the graph, and EI dot EJ is the number of times that they intersect. It'll be 0 or 1 in this picture. And EI dot EI, that's just the degree of the normal bundle. That's this minus DI that I mentioned. So I have this intersection matrix you can read off from the graph, and a key fact is that this is negative definite. So this may have been due to Wahl in the 30s. I think this was well known in the 1960s when this theory came to the forefront. So I'll just mention that's a little exercise to prove. So how would you prove something like that? Well, take some other function and restrict it to v. So let g be in the maximal ideal. So you could just take a coordinate function like x and look at its zero set up on here. So consider g equals 0 on v twiddle. And what would you get? Well, the g vanished at the origin, so g is going to vanish on every one of these curves with some multiplicity. So that zero set you can write as summation mi-ei, where these mi's are positive. And then plus some proper transform. Proper transform. So maybe it's easier to see in this picture. If you take say a coordinate function and look how much it vanishes 6 times here and 3 times here, but also it vanishes maybe a little bit there, maybe a little bit there. That you put in the C, the proper transform. But numerically, this is equivalent to 0, because it's the zeros of a function. On the other hand, this curve, the C, intersects some of these guys non-negatively. But C dot ej is greater than or equal to 0 all j. So it's some kind of exercise to say that therefore the intersection matrix VIEJ is negative definite. Okay, so that's what the graph looks like. Now, so we've seen that the graph gamma allows us to reconstruct sigma. Okay, so this graph is this thing over here, and we reconstruct the three-manifold. And actually, there exists a converse due to Walter Neumann that says that the three-manifold itself, with a couple of exceptions, of known exceptions, determines the graph gamma as well. So remember, the way we had to get this graph gamma was by resolving the singularity. But in fact, the graph is equivalent information to the this topology sigma. So what we've talked so far is the first aspect of the topology of the singularity, just this three-manifold. But we're a long way from knowing important properties of the singularity. In fact, you can check, warning sign, sigma of 2714 is homeomorphic to sigma of 3412. So this is, remember, this is x squared. Yeah, so I should have said here we have a sigma EQR. So this has multiplicity 2 and this has multiplicity 3, but both of them have a graph that looks like this. So we have a long way to go to understanding the singularity from just looking at the link. These are topological invariants. I want to mention one analytic invariant of the singularity. Analytic invariant. Well, from this very general picture, you can see there are certain obvious ones. I mean, these guys are Riemann surfaces. So they have moduli. Okay? There's more than one Riemann curve of genus G. And similarly, the normal bundle is a line bundle on this non-singular surface. So there are lots of them. But there's one important analytic invariant called the geometric genus. Geometric genus piece of G, and that's going to be the length of R1 pi lower star of the structure sheaf of V. Okay, or, if you like, it's basically the dimension of the first homology group of the structure sheaf of V twiddle. Okay? So this number is much better than the sum of all the genera. So this is greater than or equal to the sum of all the genuses you see. But even if all the things had genus 0, this can be arbitrarily large. So it turns out this one number is extremely interesting. That's the geometric genus. And we're going to be mentioning this more later. So it's not clear how to compute this. I mean, if you can resolve the singularity, if you're good at that, there's an algorithm. You can see what the graph looks like. But how to compute, not so obvious. Okay, so let's talk now about the key examples. In fact, the key example, rational double points. So this is your most basic hypersurface, a singularity. So this comes from looking at C2 mod G, where G is a finite subgroup of SU2. So this is classically known. There's a nice finite list of these guys. There are cyclic groups, binary dihedral groups, and binary polyhedral groups. So one example would be where G is just the group generated by zeta and zeta inverse, where zeta is a primitive nth root of 1. And to what we're really doing is looking at the ring of invariance. So we're really looking at C of AB. We're really looking at the ring we want to consider is the ring of invariance under the action of the group. So in this case, let's see, what are the invariants? A to the n is invariant AB, and B to the n. So there are three invariant polynomials. Let's call them x, y, and z. And they satisfy one equation, xz equals y to the n. xz minus y to the n equals 0. So this quotient, C2 mod G, is a hypersurface, and there's its equation. Okay, so if I'd started off with that, what would the link be? So the link, sigma in this case, is the quotient of S3 by the group, right? Because this is that's when I look at the distance from the origin, I might as well look at S3 mod the group, and G is an SU2. So we have that. If G is cyclic, the link here is a lens space. So in this example, what's the resolution look like? The resolution graph, it's going to be a chain like this, consisting of n-1 nodes with -2s everywhere, and they're all rational. So you might recognize the Dinkin diagram. For a sub n-1. So if you just work that out, that's what you get. And similarly for the other groups, if G is binary icosahedral, then we know from Felix Klein that there are three invariants. The ring of invariance has three generators satisfying x squared plus y cubed plus z to the fifth equals 0. The resolution diagram in this case is the Dinkin diagram for E8. Gamma equals Dinkin diagram For E8, if you don't know what the Dinkin diagram is, it's not really important. It's a familiar configuration of 8 nodes. And the link in this case, sigma, this is the famous Poincare homology sphere. Poincare homology sphere. So the story here is that the Poincare conjecture says if you have a 3-manifold that's simply connected, then it's the 3-sphere. And this theorem was proved a few years ago. Poincare originally thought, well, maybe if you have a compact connected 3-manifold whose homology is trivial, then maybe it's the 3-sphere. But he found this counterexample here where the fundamental group is not trivial. The order of the fundamental group in this case is this famous group of order 120. So this is a famous 3-manifold. So these are the rational double points. They correspond to AN, DN, E6, E7, and E8 in terms of the diagrams, and the groups are, as I mentioned before, these have been known classically. So these are the rational double points, and all of them have geometric genus 0. Okay, so that's the hypersurface picture. So we want to move now to general normal surface singularities, general NSS. So the first thing I should do is give you some examples. So we'll want some V common 0 now, and not in C3, but in some Cn. So I mean, you understand what these guys are. So what are the examples that we should be keeping in mind? Well, the first generalization, instead of having one equation in C3, we want to have n-2 equations in Cn. So these are what is called in the trade ICIS, isolated complete intersection singularity. Complete intersection singularity is called isolated. So this is given by the vanishing of n-2 polynomials. That's given by the vanishing of n-2 polynomials in n space. And of course, the thing has to turn out to be to have an isolated singularity. And if it's isolated, it's automatically normal. So if you get an isolated singularity, then it's a theorem. These are normal. So that's some good example. It's a jazzed up version of the hypersurface case. Second example that will be important are generalizations of this, quotient singularities. Quotient singularities. So here you look at C2 mod G, where now G is in U2, not necessarily SU2. And to avoid duplication, you assume no element except the identity has eigenvalue 1. But I want to run to the generalization of this cyclic quotient. So I want to look at a very special one. So suppose 0 is less than q less than n, and n and q are relatively prime. Then there's a special quotient I want to look at, which I'll call V sub nq. So that's C2 modulo the group generated like that, but with zeta to the q 0, 0, where zeta to the n equals 1. So before I did the case q equals n-1. But now I'm going to allow any q. So these are cyclic quotient singularities. So these won't be hypersurfaces anymore, except in this case. And The link sigma NQ, is frequently written L of NQ, and this is what's called a lens space. So it's a quotient of S3, again. S3 mod G. So these are very familiar to topologists. How about gamma? Suppose we resolve these guys, so we can do resolution of singularities again. Well, let me come back to that. Right now, I just want to mention examples of a singularity. So we have these cyclic quotients. Let me say 2 prime. Take any example that you know and divide out by a group. You can get another one. So V comma 0, a normal surface singularity. G, a finite group of automorphisms. Let's suppose it acts freely off the origin. Acts freely on V minus 0. Then you can form V mod G, comma 0. That's a new normal surface singularity. So quotient construction is quite useful. It's a jazzed up version of this. Okay, so that's a good example. How about a very geometric one from projective algebraic geometry? Those would be cones. So suppose you take a curve in projective space, non-singular curve in projective space, and then you take the affine cone, cone C of C, in n plus 1 space. So this is supposed to be non-singular. Right, so that just means, it means what you think it does. It means you just look at the defining equations for this curve in this space, and instead of viewing, when you look at homogeneous generators here, but the actual polynomials over here. So this is what you think a cone should be, and this has an isolated singularity. It's a surface. So this is an isolated surface singularity. However, it's not normal in general. Isolated, not normal in general. So classically, one studied what were called arithmetically normal curves, and that just meant that this cone here was normal. So you need that the embedding it's sometimes called projectively normal, or arithmetically normal. So if it's not, you would just take the normalization. So you take the normalization. Take the integral closure, and then you'd have a normal surface singularity. So what you're really doing over here, and what this turns out to be, have a coordinate ring that's a direct sum of all the twists of this line bundle. This, in fact, is the normalization of the cone. See, the cone was a quotient of the homogeneous polynomials here, and if it's not projectively normal, this is more. So we can jazz this up even further to make an example of a general cone. You take C non-singular and L, a line bundle of positive degree, and then look at the ring, well, say spec of direct sum of gamma of C comma L tensored with itself k times. K goes from 0 to infinity. So we call that V. So this is what we mean by a cone, something you can build out of a non-singular curve and any line bundle of positive degree. So this is again a cheap way to make normal surface singularities. So now we know some examples. What can we do with them? Well, we can do the same thing that we did over here. So as before, you can define the link, sigma, so it's V now intersect some huge sphere. But again, a compact connected three-manifold. So again, that's connected. It's a three-manifold. You can have resolution, V twiddle E into V comma 0. Have good resolutions. The fact that it was a hypersurface doesn't matter. In fact, it's not even an easier theorem to prove the existence of a resolution. So we have this in the case of normal surface singularities. We have this intersection matrix, EI dot EJ, which is still negative definite. You have the graph gamma, which you can make from a resolution. You have the theorems of Mumford and Walter Neumann. And you can define the geometric genus. I'll say H1 of OV twiddle. So everything that you did in a hypersurface case, you can do it in this incredible general situation. So what's the moral? The moral is that the hypersurface case is really complicated. From this point of view, the fact that it was defined by one equation does not mean that the geometry and the topology was particularly simple. So in fact, I took an example here because it looked easy, but it's actually quite difficult. And I could have just started with normal surface singularities and defined this over here. And Mumford's theorem and Neumann's theorem and everything else. The proof did not use the fact that it was a hypersurface. So let me just mention in these examples that I did before, what does the graph look like? Well, in this case, it's as complicated as a hypersurface, can't say. But for quotient singularities, there's a nice answer. You always end up with a chain of rational curves. This is what the resolution looks like. These are all rational curves. So here's gamma. And how are these numbers related to n and q? Well, by this continued fraction expansion. b1 minus 1 over b2 minus 1 over b3. That's n over q. So that's a little trick that tells you what these numbers are. So remember, in this case, they're all minus 2's. But in general, you can have anything you want there. So that's what the graph looks like in that case. How about for a cone? How about in this case? Well, the resolution is quite simple. The resolution is the geometric line bundle. So in this case, V twiddle is the geometric line bundle over C. So what we really have is V twiddle over C, and then you can collapse the zero section to V. So you could start with the curve, take the geometric line bundle corresponding to L, take the zero section and collapse it to a point, and that's how you make the cone. So in this case, the graph looks like this curve here of genus G, and then you have a minus D there, where D is the degree of L. So this is these are some particularly easy ones. So So now we've finished with, with topology, and now we should have a real serious conversation with ourselves of what we're facing. Well, so there's a result of Grauert that says, Grauert, any gamma, take any graph, it's got to be negative definite, and stick into it actually not just a graph, but your favorite Riemann surface for each curve and your favorite normal bundle whose degree matches the graph. Take any gamma with any EI and normal bundles. So he says there exists a singularity, a normal surface singularity, V, giving this a gamma, and these EI and normal bundles. So in some sense, there's a complete classification. So any gamma occurs for some normal surface singularity. This is any graph. Now you can make a negative definite just by throwing sufficiently large negative numbers at each node. So what you end up with is a zoo with too many animals. So what you have to do is introduce some appropriate properties that graphs or singularities can have to get away from the incredible generality that you might have. So I want to talk about different properties of a singularity that pin you down a bit and give you a chance to at least make plausible statements. So, special properties. So the first one I'll mention would be the equations. You can look for something with nice equations. So what you want to do is consider the possibility. I want to look now at what I call the weighted homogeneous case. Weighted homogeneous, or sometimes called quasi-homogeneous. So this is the case where instead of just looking at a germ, we've got a nice graded ring. Suppose we have A, some graded ring, which is going to be a two-dimensional normal domain, but it's graded and generated in degree 0. So it's C of Z1 through Zn modulo some equations. And these Zi's have weights. The weight of Zi is Wi. And with respect to those weights, these guys are homogeneous. So F alpha of Z is weighted homogeneous. So this is a particularly nice class of equations. Weighted homogeneous, you presumably know what it means. This is a whole variety, so while I write V equals spec A, that's a whole affine variety. And we're interested in germs. We want to look at the analytic local ring. And so we want to know something that's analytically equivalent to one of these, and that's what quasi-homogeneous means. Quasi-homogeneous means analytically equivalent to essentially A hat. So why are these good? What's so special about these? Well, what we know, what we can understand because of the grading, is that V has a C star action. So this variety, this affine variety, has a C star action. where the origin is the only fixed point. Okay, that's what it means for this to be graded. And we can look at v minus the origin and divide out by the C star action. The action's free there, and we get a curve, non-singular curve. It's a projective non-singular curve. So we want to understand this singularity, at least from the point of view of what we've been talking about before. What's a resolution look like? So what's a resolution? Well, instead of resolving it all at once, there's something natural to do called a weighted blow-up. I won't say what it is. Weighted blow-up. So you end up with some v prime into v, which is not non-singular, but it has the curve E sitting on it, and it's got some cyclic quotient singularities over here. So these are cyclic quotients. So v prime is what you would call a partial resolution. Partial resolution. So this is a theme we're going to meet up later. Sometimes when you have a singularity, rather than resolving it all the way, there's some natural God-given space that's part way to a resolution. And we have that in this case. By some algebraic trick, it produces this curve and these cyclic quotient singularities that we already know how to resolve. Okay? They'll have resolutions like that. So when we finish resolving, what do we have? We'll have this curve here, and then we'll have these chains of rational curves like this. So in terms of the graph gamma, we're going to have this central curve here with some genus, and then we're going to have these nodes coming out like this from the cyclic quotients. So this is what so gamma, I would say, is star-shaped. So a quasi-homogeneous singularity has a star-shaped graph, and the central curve is proj of A, or if you like that, or what you get when you divide the graded ring out by the C star action. Maybe I'll write that for those who like proj. So very special graphs.
J is non-singular.
No, that's automatic in this case. It's automatic in this case because it's a two-dimensional quotient by a C star action. C star action is free off the singular point.
Every plane curve is non-singular.
This isn't a plane curve. This is dimension 2.
In particular, every plane curve is non-singular.
This is correct. Let's talk later. The dimension of A is 2. Quotient singularities in dimension 1 are non-singular. That's basically it. One nice thing about this is when you see this picture, this is topology. There's a lot of analysis there to writing the whole thing down, but for a weighted homogeneous singularities, you know what else you need besides the graph to recover A analytically. So A analytically is equivalent to the graph plus the isomorphism type of E plus the normal bundle, which is a line bundle. Normal bundle. And finally, this central curve, you've got a whole bunch of points that have been picked out where these chains go off. So you have some number of points on a curve. So if you have like 4 points on P1, there's a modulus there, plus the intersection points. So in this case, you can really see the whole singularity from the graph, plus this very specific extra information. So that's one important special property. Second special property. How about having graphs with only rational curves? In fact, rational curves with no loops. So let me call that QHS link. This means rational homology sphere. That means gamma is a tree of rational curves. So those are the simplest graphs, or trees. So that means the topology is much simpler. And you don't have to worry about positive genus curves and line bundles. So this is an important class of singularities about which we might want to say something. Those where gamma is a tree of rational curves, no loops and only rational curves. So number 3 is related to that, and we want a small genus. So remember, we have geometric genus, small PG, small geometric genus. So that's the definition. So definition, v comma 0 is a rational surface singularity. If PG is 0. Okay. So that's an analytic definition because R1 pi lower star, I mean, this is analytic. Maybe I should have mentioned that V of 2, 7, 14 and V of 3, 4, 12, these have different PG. So this was same gamma, different PG. So geometric genus is definitely an analytic invariant. So if it's 0, we'll call it a rational surface singularity. So some examples were the rational double points. The rational double points I mentioned, I didn't prove. Those were rational singularities. So a rational singularity in particular has QHS link. So this implies QHS link. So the graphs of these things looks like that, but the theorem due to Michael Artin, again in the early 60s and starting the subject, and that is there's a topological way, just looking at gamma, to tell whether it's rational. You can read off rationality from gamma. So in this case, the topology tells you that this analytic invariant is 0. So what do you have to do? You have to play some game with the intersection matrix. So I'll just say quickly what that is. So you find the smallest. So for every gamma, find the smallest z equals summation ni ei, where the ni are greater than or equal to 0, with z dot ei less than or equal to 0 for all I. So if you give me a graph, you can fool around, and it's negative definite, you can find such a z. And now you ask, is z dot z plus k equal to minus 2? So you can ask this question for any graph. So I hear you say, what's k? Well, k is supposed to be the canonical line bundle on v twiddle. But in order to compute this, I mean, z dot z, you know ei dot ej, you just need to know what's k dot ei. So k dot ei is what you think it should be given the adjunction formula. K dot ei plus ei dot ei equals twice the genus minus 2. So if you like, that can be a definition of what k dot ei is. That's the adjunction formula. And therefore, you can figure out k dot z because that's summation ni k dot ei. Anyway, so here's the criterion. You take a graph, if it satisfies that, Michael-Artin's theorem is yes. So it has a rational singularity. So let me show you how many, that there are lots and lots of rational singularities. So example, take any tree and arrange such that at each node, this number di is greater than or equal to the valency. Valency means number of things that intersect. So take your favorite graph. So there's the tree, but it's not weighted yet. So what I have to do at every one of these is make sure I put in something that's at least minus 3. So the di I put in, the valency is 3, so I should have a minus 3s over here. Okay, over here, I'd have to have at least a minus 4. Minus 5 would do. And then you can put in anything you want at the others. If you do that, it's rational. So if I do something like this, minus 1, minus 2, minus 3, minus 7, that's negative definite. You can check. But it's not rational. This is QHS link, but this is not a rational singularity. But there's a topological criterion, and there are lots of these rational singularity graphs. What else did I want to say? Yeah, so let me point out one of the important things about rational singularities. I mean, so what's so great about that? You can recognize them. Well, you can say a lot about the singularity itself from the graph. You can talk about analytic properties from the graph. So for a rational singularity, you can read off the Hilbert function. So that means the embedding dimension, the multiplicity, the whole Hilbert function. You can find out about, you can write down equations. I'll put write down in quote equations. You can write down equations for singularities with a given graph. Up to action of a group. That's not something I'm going to go into. And you can put all v comma 0 with the same gamma, because you can have lots of rational singularities with the same graph, but you can put them all together into one nice equisingular family. Put all those into one non-singular, equisingular family. I shouldn't say non-singular. You can one equisingular family over a smooth parameter space. So that's one of the things that's so nice about rational singularities. So maybe I'll stop now. When I get to this afternoon, I'll start. There's one topic to finish, and that's the Gorenstein property. The Gorenstein property of normal surface singularities. That's a property that hypersurfaces have, complete intersection singularities have, in general, one doesn't have that property, but it's a very interesting analytic property. And I always tell audiences, if you don't know what Gorenstein is, Dan Gorenstein didn't know what the property was. I mean, he was a student of Zariski, and he did something, he did some very nice work there, and then he moved into group theory. But it was either Hyman Bass or probably Sayre who took that property and applied it in general to rings and called it the Gorenstein property. So we'll start on that this afternoon and then move into the question of smoothings. Okay, I'll stop.